Okay, let's get started. Welcome to the HAO Colloquium, and today our speaker is Dr. Tim Bastian. And is on? Is it on? I thought it's a green.
Green light? Okay.
Go.
Speak up anyway.
Okay, all right. Better now?
Yes. Thanks.
So Tim got his bachelor degree in math from the University of Chicago, and then his PhD in astrophysics from CU, working with George Dalk. And then he went on to National Radio Astronomy Observatory as a Jansky Fellow, and later joined the staff as an astronomer. And he has served as the Assistant Director for Scientific and Academic Affairs at NRAO, and now he's the head of the Department for Science Support and Research. And today he's going to talk about, the name changes. Fast,
Did I change the name?
remember, it's like fast imaging.
It's dynamic. It's a dynamic.
Right. Oh, and I was told, Reed said even in this small room, we need to use this to ask questions because this is very unidirectional, so cannot pick the signal very well. So if you have any questions, let us know and we'll pass this around.
Okay, thanks for the intro. As the title suggests, I'm going to talk about imaging spectroscopy at radio wavelengths. I'm of the radio persuasion. There are lots of old friends in the room who also do radio. Nariaki is a lapsed radio astronomer. Perhaps you can get straightened out through rehab and rejoin. And Al goes way back. I haven't seen Alan Kiplinger. Oh, and Terry, you can't get off the hook. Also did some work in radio. What I thought I'd do is, because I'm aware that not everyone is a radio astronomer, I'd offer a little bit of introduction and motivation for what I'm going to describe today, and then spend the bulk of the talk on sort of the early steps we're taking, tentative as they are, towards fast imaging spectroscopy, using solar flares as a particular example. But it's a technique that others, of course, have recognized as the way forward in their various wavelength regimes. I'm using flares as an example because that's where a lot of the preliminary work has been done, although I should mention that people like Stephen have been exploiting this sort of technique for active region observations as well. So, as I say, using flares as the platform for examples, I'll talk about some data from the Owens Valley Solar Array, from the Novayama instruments, from the FASR Subsystem Testbed, which is a little 3 antenna interferometer, and then some early observations from the upgraded VLA, the Very Large Array, or the Jansky VLA, and then I'll conclude. So, because not all of you are radio astronomers, I thought I'd just make a few remarks about radio emission mechanisms and the propagation of radio waves in the sun's atmosphere, just to orient you. I think it's not a surprise to learn that the sun's atmosphere is a magnetoactive and highly dynamic plasma. As such, it has various natural frequencies associated with it, and two of the fundamental frequencies that happen to be a very good match to radio frequencies are the electron plasma frequency. And just to remind those of you who this is not your currency in trade, if you have an ionized hydrogen slab, electrons and protons, and you separate it slightly, electrons here, protons here, you set up a charge separation and electric field. So there's a force, an electric force. You let them go, the electrons rush to the protons, overshoot, the electric field reverses back again, and an oscillation is set up. That's a plasma frequency. Now, because the corona has a finite temperature, the waves are in fact dispersive. They can travel around, they can interact with each other. Plasma waves themselves are non-propagating out to infinity. They can't escape the corona, but they can convert to other modes and escape the corona. The other natural frequency I want to mention is the electron gyro frequency, which also finds itself in the radio regime. It's about 3 megahertz times the magnetic field in Gauss, so 100 Gauss field. The gyro frequency is a few hundred megahertz. Okay. And then finally, of course, there are collisions between electrons and ions. And these three frequencies form the basis for radio emission mechanisms: plasma radiation, and I'll show you an example in a moment, gyro emission, and the term we use to describe the gyro emission depends on the energy of the electrons. For a thermal distribution of electrons, we refer to thermal cyclotron or thermal gyro resonance emission. And that happens at low harmonics of the gyro frequency, the first, second, third, maybe fourth harmonic or integer multiple of the gyro frequency. If the electrons are mildly relativistic, so tens of keV to MeV energies, then we talk about gyrosynchrotron radiation. And that's highly relevant to solar flares. And then in cosmic sources, sidereal sources, synchrotron radiation is the term we use for ultra-relativistic electrons gyrating in a magnetic field. And then, of course, free or Bremsstrahlung radiation is ubiquitous in all astrophysical objects, and the sun is no exception. So there's an example of what the sun looks like. Mostly thermal free radiation here. That's at 17 gigahertz. This was made with the Nobayama radioheliograph in Japan. If you look carefully, you can see that the poles are brightened relative to the rest of the quiet sun. You can see the active regions, first because the density is enhanced, but also there may be a gyro resonance component where the red spot is, where the magnetic field is strong enough to render the corona optically thick to gyro resonance absorption. Here's a detail from the VLA from Stephen White, showing in the background the white light continuum image, and then overlaid at 3 different frequencies is the corresponding gyro resonance emission, which you can think of as a brightness temperature map on the isogauss surface above the active region. And so depending on the frequency, you're basically tuning up and down in the corona, high frequencies being low in the corona at higher magnetic fields, low frequencies higher up in the corona and lower magnetic fields.
That image on the left, Tim, have you actually masked out the region above the limb?
No.
So there really is no significant emission.
It's it's just a few hundred Kelvin at 17 gigahertz that the corona is contributing. That's all chromospheric emission for the most part, except in the active regions. Then in the lower right is an example, again from Nobayama. On the left-hand column is 17 gigahertz images of a flaring loop. So we're seeing gyrosynchrotron emission from the trapped MeV electrons. On the right column is the same thing, but at 34 gigahertz, an octave higher in frequency. And then in between is the polarized emission at 17 gigahertz, superposed on a magnetogram. And then finally, here's an example, not an image, but a spectrum from the Green Bank Solar Radio Burst Spectrometer, showing frequency on the vertical axis. So it's a spectrum at any given time, and then time runs from left to right on the bottom axis. And you can see some very fast, almost vertical bursts at the extreme left. Those are so-called type 3 radio bursts, plasma radiation due to non-thermal electron beams propagating in the corona. And then you see a slow drifting pair of lanes, emitting lanes. That's a type 2 radio burst, which is a shock driving this emission in the corona, often associated with fast coronal mass ejections. And so type 2s especially you hear lots about in connection with space weather. Just a quick reminder, because the sun's atmosphere is a plasma, the magneto-ionic modes are relevant. The modes that escape to infinity are the extraordinary and ordinary modes, which manifest themselves to the observer as right circularly polarized and left circularly polarized emission escaping the sun. But for those emissions, or those waves, like Whistler waves or Langmuir waves is what the L stands for, or Z mode is sort of a generalized Langmuir wave or plasma wave, those do not propagate. They need to be converted to other wave modes, to transverse wave modes, as I mentioned earlier. As far as imaging spectroscopy is concerned, as I said, I want to use flares as my example because there's such a rich phenomenon. There's so much physics that takes place in a flare, from magnetic energy reconnection to particle acceleration, particle transport issues, and so on. Not to mention lots of microphysics in the plasma domain. So here's a cartoon from Marcus Ashwaubenon and Arnold Benz from way back, but I like it just because it summarizes the cartoon nicely. Energy reconnection taking place through mysterious means in the shaded oval. Down low, fast electrons stream down to the chromosphere and are stopped on the dense cold chromosphere and produce hard X-ray emission. So this is real data from RESI. The two green contour footpoints are 25 to 40 keV emission illuminated, and then the color there is 4 to 9 keV, sort of quasi-thermal emission, which you can see flux piling up at the loop top. The same flare was observed in microwaves. This is the 34 gigahertz image at the same time, and you're seeing the magnetic field illuminated by MEV electrons trapped in the magnetic configuration. You can easily see the two legs of the loop system illuminated in radio. And then in between, if it were darker, or if you could play with it a little bit with the contrast, you would see a quasi-thermal cusp-like structure forming in between. It's actually quite fascinating to see the movie. All right, well those are sort of what's going on low down in a flare. If we look higher up in the energy release region or above, we have, and now I'm switching to a spectrum, we have all manner of radio bursts, including the so-called type 3 bursts, multitudes of electron beams which stream away from the reconnection site, or at least that's the way we've been interpreting what we see in the spectra. Shown here are so-called reverse slope type 3 radio bursts, meaning the beams are streaming from high to low. The classical type 3s stream from low to high. In other words, they're propagating up in the corona. So lots of rich structure in a flare. Just speaking very broadly, we can sort of distinguish between two spectral components above a few gigahertz. Essentially all flares show an incoherent gyrosynchrotron component, so fast electrons interacting with the local magnetic field. So you see right away where and when non-thermal electrons are present. Lower down, for about 25–30% of flares, coherent emission mechanisms play a role. Now they have been known, many of them have been known for decades. The frustration has been identifying the actual emission mechanism. It's non-trivial, in fact. And with imaging spectroscopy, I hope to show that we can make some progress there and in fact leverage information out of these mechanisms. So dynamic imaging spectroscopy, it sort of reminds you of the image, of the old quote from Jesse James when asked why did he rob banks? Because that's where the money is. And why do imaging spectroscopy? Because that's where the information is ultimately. I mean, we've known and loved radiodynamic spectroscopy for decades, right? It goes all the way back to the late 1940s, early 1950s. A record of intensity as a function of frequency and time. And you can see these patterns which can be interpreted in terms of physical phenomena. Similarly, at high, we were able to produce high-resolution images at radio wavelengths. The sun looks like the sun, surprisingly, at radio wavelengths. We use Fourier synthesis to do so. So we use lots of pairs of antennas to measure Fourier components of the brightness. We invert that and then get an image. So that's an image of the sun now at 4.9 gigahertz from Stephen at the VLA. But of course, we want to combine the two as a means of more fully exploiting what really is a rich vein of information combined in the entire domain of time, frequency, and angular resolution, not to mention polarization. So the idea then is for every time and frequency in a dynamic spectrum, yeah?
The question is pictured from the VLA that you showed. How is it taken? It's a snapshot?
Well, that's one of the downsides of using the VLA, which has 27 antennas. 27 antennas produce 351 pairs of antennas instantaneously. So 351 Fourier measurements. That's not enough to characterize the brightness temperature of the sun in a snapshot. So in fact, you use the Earth rotation to fill in your aperture. But of course, the sun rotates, the sun twinkles and does other complicated things. And so you begin to smear things out. And even more so, I mean, Stephen did this using the 6-centimeter system, where the field of view is only 9 arc minutes. So he actually had to do something called mosaicing, meaning many pointings over the sun combined in a nonlinear deconvolution algorithm to produce the image.
Okay. That's a real filament channel at the bottom there. It's a real filament channel.
Yeah, it's a beautiful image.
It's supposed to look that good. Yeah, they're a mystery in the radio. It's a jet on the field.
Yeah. All right, so it's a fairly obvious idea, but the implementation is, shall we say, challenging. For the spectrum I showed you, the dynamic spectrum, it's basically for every pixel in that spectrum, for every time and frequency, we want the corresponding image, the high-resolution image. Or for any given image at any given time, we want the polarized spectrum. And in so doing, it enables us to unambiguously identify relevant emission mechanism or mechanisms. There are often many emission mechanisms which are going on. Exploit fundamentally a new diagnostic technique. For example, coronal magnetography has been a holy grail for both the optical IR and radio communities. Study the spatial, spectral, temporal evolution of sources, and study fundamental phenomena as coupled systems. I mean, I think it's really, I'll come back to this point later in the talk. And as I say, I'm going to use flares and jets, active phenomena, as motivating examples. So the first example actually is from Nobeyama in Owens Valley. This is somewhat old work, but I think it's relevant to this issue of dynamic, of forward fitting and spectroscopy. Many of us are here in Boulder this week, in fact, for doing forward modeling of quiet coronal phenomena, specifically coronal cavities, with Sarah Gibson's suite of software called Forward. This is another example of a kind of forward modeling or forward fitting. So I chose this example because it's a deceptively simple example. The paper came out in 2007 with Gregory Fleischman and Dale Gary. It's a rich data set, a rich observation of a simple flare. We have spectroscopy from Owens Valley, 1 to roughly 15 gigahertz in Stokes I polarization, total intensity. We have at Nobeyama fixed frequency polarimeters. That just means we measure light curves in Stokes I and V as a function of time with 100 millisecond time resolution at fixed frequencies from 1 to 80 gigahertz. And then finally we have imaging at Nobeyama at 17 and 34 gigahertz with angular resolution of about 10 arc seconds and 5 arc seconds respectively. And then supplementing this we had, GOES and Yoko and a little bit of trace. Right away this flare looks a little peculiar because if you plot, this is analogous to Kasugi's old diagram using SMM, I guess it was. If you plot the peak 17 gigahertz flux versus the HXT L band here, not particularly hard, M band would have been preferable, you get a scatter plot with showing a nice trend. And you see that the flare I'm going to talk about today from 2001 is, in terms of radio emission, is fairly impressive, a few hundred solar flux units, but in X-rays it's very X-ray poor compared to most other flares. And so that tells you something, not sure what yet.
Those are just different flares, those points.
Those were all of the flares observed jointly by Nobeyama and by Yoko, HXT. So here's what the flare looks like. On the left side is the light curve, the radio light curve compared to the GOES soft X-ray light curve in the 0.5 to 4 angstrom channel and the HXT 12 to 23 keV channel. And you can see it's extremely simple. It's very impulsive, only lasts a couple of minutes. In X-rays it shows the nice sharp spike. In radio I'm showing the normalized 17 and 35 gigahertz on top of each other, and they're essentially indistinguishable, showing a nice exponential decay. And then the GOES is delayed somewhat and shows a somewhat raggedy decay simply because there's so few counts. It's very X-ray poor. And then there's a detail shown on the right side, a little bit more about the unnormalized radio light curves now. By the time we get up to 80 gigahertz, it's pretty noisy. But the striking thing is that 17 and 35 look very similar, and they track each other in the exponential decay. At 9.4, you see that the maximum is strongly delayed, and then it starts to track the radio at higher frequencies. And at 3.75 gigahertz, there's nothing, no emission at all. So what cuts it off? What stops the radio emission? Well, this is highly reminiscent of a paper that Stephen did many years ago. which Hugh Hudson and James Ryan subsequently dubbed an impulse response flare in their review in NRAO in 1995, where you see this incredibly impulsive rise, exponential decay. The light, at most frequencies, the light curve just lies right on top of each other, and it cuts off strongly below 5 gigahertz. So a similar kind of event, this one was interpreted in terms of a very dense plasma environment, and likewise, the October 2001 flare takes place in a very dense environment. So what's it look like? Well, here are the images from Nobayama, 17 gigahertz in the upper left, and you can see that it's just a nice, simple loop or bundle of loops spanning a bipolar region. The middle frame shows the polarized radiation, and so you see that the sense of polarization changes as it goes from negative polarity to positive magnetic polarity. And then with somewhat higher resolution, the source looks essentially the same at 34 gigahertz. And that's what it looks like throughout the event. It doesn't really evolve much. It turns on, it decays away. And then below are the same images, it's the same background magnetogram, and then the trace frame, the SXT, is shown in the middle, and then the HXT L band is shown in the lower right. Again, very simple morphologically. Unfortunately, we only have HXT L band counts. They were so few that it didn't trigger flare mode, so we know nothing about the higher energy photons. Here's a bit more detail of the radio and hard X-ray light curves. Again, on the left side, you see the hard X-rays turn on first. And then if you look at frequencies above 12 gigahertz or so, let's see, there's no pointer, is there? Each of the light curves is labeled with a frequency, and the instrument O stands for Owens Valley, N stands for Nobayama. And you see that above 10, 11 gigahertz, that the onset is systematically delayed as we go to higher and higher frequency. And sort of intuitively, we know that the higher frequencies are due to higher energy electrons. This suggests that the higher energy electrons are delayed relative to the lower energy electrons. But the opposite takes place as we go to the right-hand side, where we're looking at the decay phase of the flare from maximum. And you see that, again, 17 and 35 gigahertz light curves lie right on top of each other. Thanks. Right on top of each other here. And then as we go down in frequency, you see that they're progressively delayed. It's where the maximum is. So what? Yeah.
So if the hard X-rays come from impacting of energetic electrons onto denser plasma, why don't you see them after the signatures in the radio?
The energy of the electrons producing the HXT low, so roughly what, 13 to 23 keV, are low energy, and as I'll explain in a little bit, the density here is about 10 to the 11 per cc, and so it's collisionally thick to energies that are so low energy, meaning they never make it to the foot points. You saw that there were no 2 foot points. It was just a sort of quasi-uniform source. So the loop itself is collisionally thick to the HXT L band electrons.
So what my question is just simply, what does those observations say about the thick target model?
Well, the loop itself is thick, meaning the energy is being deposited up in the low corona, rather than the electrons being able to propagate all the way down to foot points. Okay, I'll come back to that. This is again a dynamic spectrum. This is from Owens Valley, so time here, frequency here, although instead of megahertz, we're looking at gigahertz, so about 4 gigahertz up to 15 gigahertz here. And so we see the emission at each frequency as we go from across in time. And if you look carefully above 12 gigahertz or so, you see this effect beginning to show itself of the onset being slightly delayed. And then this dashed line shows that the time of maximum is progressively delayed as we go to lower and lower frequency. Now, this is sort of the opposite of what we usually encounter, because usually the density environment is far lower. The trap plus precipitation model often can characterize the time evolution of the particles pretty well. In other words, the fast particles get trapped in this magnetic bottle. Collisions are inevitable and scatter them into the loss cone, and they precipitate. So because the collision frequency goes as energy to the 3 halves, or velocity cubed, the more energetic electrons tend to hang around in the trap longer. So high frequencies tend to peak later than low frequencies, whereas we're seeing the opposite here. So why is that? Well, the interpretation here is that the radio emission is indeed due to gyrosynchrotron emission from non-thermal electrons, but the plasma itself is relatively cool and dense. The ambient plasma density is high, and therefore something called Racine suppression is relevant, which suppresses the low frequency part of the spectrum. And also because of the presence of this dense, cool plasma, free absorption has to be taken into account as well. So any source function has to include the contributions of both thermal plasma and the non-thermal electrons. So the idea here is coming back to this idea of electrons depositing their energy in situ rather than propagating down to the foot points and dumping it in the chromosphere, is that the energy lost by fast electrons heats up the ambient plasma. As it heats up the plasma, the opacity, the thermal opacity drops, and you get this reverse delay structure as a result. So we set about modeling this using forward fitting. We have spectral data every 2 seconds with Owens Valley. Unfortunately, the flux depends on lots and lots of parameters. We chose, it's the frequency, the magnetic field, the orientation of the field, the temperature, the ambient density of the thermal plasma, and then the properties of the non-thermal distribution of electrons, the power law index, the number density, and the cutoffs associated with that power law. And we don't have enough data to fit all of those things. Of course, the aspiration is to fit for all of these things because we'll have much, much more data. But because we don't have even polarized data, we just have to fit to our total intensity data from 2 different instruments, we have to be a bit more modest. Luckily, the flare is simple, right? And we model it basically as 1 pixel. That's a uniform rectangular box. And then we know the area of the source, we know its distance. We can guess the magnetic field, but that's one of the things we vary. We can guess the plasma density, but it's another parameter we can vary. We don't know a priori the number of fast electrons. We don't know a priori the temperature. So, as I said, the absorption and emission coefficients have to comprise 2 parts: the contribution of the free absorption or emission, and the gyrosynchrotron. And for most of the fitting, we allow these 2 quantities to vary, temperature and number of fast electrons, and then we fiddle around with 3-parameter fitting, or simply hold things fixed and try different trials. Just to sort of orient you a little bit, there is lots of information packed into the gyrosynchrotron spectrum. The solid line shows what the spectrum looks like in the absence of any plasma at all, so the gyrosynchrotron emission in vacuo. But then if we set the density to 10 to the 11 and the coronal temperature to 2 megakelvin, and then allow the magnetic field to vary, you see that both the peak and the flux depend sensitively on what we assume about the magnetic field strength. We can play the same game by now fixing the magnetic field at 150 Gauss and tuning the ambient density up and down. And you see that when it's only a couple times 10 to the 10, there's just this modest little cutoff here at the lowest frequencies. But as we crank it up, you see that it cuts off emission below, a few gigahertz. And as we crank it up even higher, it totally quenches the gyrosynchrotron emission. And you can see at the highest frequencies, the free emission is coming up. And then finally, one other example, if we now fix the magnetic field and the ambient density and let temperature change, at the lowest temperatures, the quenching is strong, the peak, the spectral maximum is over at a higher frequency, and as we crank up the temperature to 20 million degrees, the thermal absorption decreases, and the peak, the spectral maximum drops to a lower frequency. So here's the fitting. 25 different spectra separated by 2 seconds. We did a chi-square minimization. The spectra are comprised of both Owens Valley and Nobayama data. I'll come back to this point. We used actually an approximate scheme to speed things up, to do the calculation of the gyrosynchrotron emission absorption coefficients, because they're somewhat hair-raising and computationally very expensive to do it exactly. As I said, we did 2 and 3 parameter fits. In 3 parameter fits, we would vary delta, the spectral index on the non-thermal electrons, or the cutoff energy. We found that the density, even though we would allow it to vary, was robustly high at about 10 to the 11. It didn't really matter much what we assumed. It stuck around 10 to the 11. So we fixed that. We also, as I said, let delta vary. It maybe led to some modest increases. All three fits are shown here. For the most part, you can't really see much difference between the 2 and 3 parameter fits. It didn't lead to any notable improvement, really. So here are the results for forward fitting to temperature and density. You can see that the fast electrons simply track the light curves at the high frequencies. Not too surprising. And then the temperature starts out low at about a couple million degrees, and then increases through this impulsive spike up to about 10 million degrees, at which point it flattens out. So the fitting, using the data themselves, confirm our suspicions that thermal absorption had a role to play here. What we'd, of course...
What's on the y-axis? You've got density of the fast electrons.
These are the number of fast electrons greater than 100 keV with the power law parameters given to the model. And I should also mention that the gray is these are the 3 values of magnetic field assumed. If the magnetic field was 150, so the dashed line here in both cases corresponds to magnetic field of 165 Gauss B magnitude, and then 150 and 180 define the gray envelope. So if the
1 in 10 to the 4 electrons has an energy above that.
Correct. Although it's a normalization, I mean, the power law may in fact extend to lower energies still, but as I said, below about 40 keV or so, the loop is collisionally thick, and they just dump their energy in the loop. And in fact, are, we believe, responsible for heating the plasma from 2 million degrees up to 10 to the 7 or so.
Just a dumb plasma physics question. If you take the volume above the plasma, and somehow you put an electric field in it to accelerate some particles, how does it know only to accelerate certain electrons and not other ones? Is that a quandary at all?
Well, first of all, it's a very small number of electrons, 1 in 10 to the 4, as you say, roughly speaking. The electrons doing the emitting at microwaves at 17 and 34 gigahertz are actually way out in the tail. They account for about 0.1% of the energy. They're out at MeV energies. We don't really know very much about the low end of the tail. Ultimately, if the density really is 10 to the 11, then they're going to dump their energy. They won't get accelerated very high. Those that are somewhat above 40 keV will be rapidly losing their energy in the plasma. But the mechanism for doing that, we have relentless speculation at the end of the paper that it's actually turbulent acceleration, and there's some scaling arguments that you can look at.
You'd think that in a plasma like that one electron is the same as the other, so it must be something to do with either loss of energy as it propagates, or it must be due to the fact that you're picking certain volumes of the electron in the plasma to accelerate particles in. Otherwise, you'd end up with 10 to the 11 electrons moving fast, right? Or not?
Well, if you had a more tenuous plasma and you had a supercritical Dreiser field, you could, in principle, accelerate all the electrons. Yeah. They'd all run away, right? But very few people believe that, super Dreiser electric fields are responsible for acceleration in flares, where, in fact, the needs are typically much more modest. Only a tiny fraction, a tiny tail of the electrons get sent way up above the Maxwellian.
But people think that that's due to a very small volume of the plasma being subjected to a very powerful acceleration. So it's a very, very small volume filling factor of very strong fields that accelerate particles, or what? I mean, that's what I'm trying to get at.
I personally think, I'm not going to sort of make something up on the spot. My personal feeling is that no, that the acceleration mechanisms are more volumetric than that. So, all right. So yeah.
What's the highest energy of electrons in your spectrum?
Well, we did fiddle with the cutoff, right? So it's a power law.
High energy cutoff.
We had a high energy cutoff, and for the calculation I showed you, it was 2.5 MeV.
My question is, if you have a hypothetically high sensitive gamma ray detector, do you think we can see it in gamma ray emission? Electron Abrams-Strong?
Yeah, I mean, if you have infinite effective area, sure.
AMS2 or something like that.
Yeah. I mean, I mean that's the contributor to the continuum in gamma rays, right? Is electron ion, even electron Bremsstrahlung.
I'm trying to get a feeling for the field line convergence. What do the magnetograms show compared to the 165 Gauss?
That it's a plausible value, but not much more than that. But what I hope to convey with this is that these are sort of the first baby steps towards trying to quantitatively model and extract information from spectroscopic data where it's not true imaging spectroscopy, but the imaging was used as a constraint to the model domain. In other words, we were able to simplify because the flare itself was quite simple morphologically. Now, of course, we may have just not had sufficient resolution to resolve all the complexity, but that's another story. But what I wanted to mention is recent developments which are being motivated by these kinds of considerations. I think something that really cannot be underestimated is some progress made by Gregory Fleischmann, who worked with us on the example I showed, with Kuznetsov just a few years ago in developing fast approximate codes for doing the gyrosynchrotron calculations. I mean, the exact calculation involves summing over multitudes of harmonics of Bessel functions and derivatives of Bessel functions, and it's very compute intensive and it takes forever. Even in the 80s and 90s, for a simple homogeneous source, it was very expensive and various approximate techniques were developed. So now we can, in fact, analyze sources pixel by pixel, fitting each line of sight separately, because there have been gains by orders of magnitude in these synchrotron codes. And not only can they handle isotropic cases, but they can handle anisotropic cases. We know the distributions are anisotropic in some cases. And, the accuracy is better than 1% most of the time. And another thing, and this sort of echoes what Sarah and colleagues are doing in optical IR, powerful tools are being developed to model radio sources, incoherent radio emission, and to visualize. We talked earlier this week about the need to have these visualization tools because we need to gain some intuition about what these sorts of data are telling us physically. And so you have to be able to manipulate the data in various ways to do so. So Jay Lunita and colleagues have developed a nice IDL-based package called GX Simulator. So you need to respond with, forward turbo or something like that. As I said, it's kind of akin to forward. It's a nice package that allows you to look at things. Here's a snapshot from the code showing that you can populate a model loop with fast electrons. You can add an atmosphere. You can look at it from different aspect angles and do the calculation. You can put in real data eventually and do the same thing. Another piece of progress that I think is very important is on the instrumentation side. The Owens Valley Solar Array, which I showed you the spectroscopic data from, is being expanded. It's about a $5 million project, 3 years duration. It's finishing up as we speak. I think the money runs out at the end of the week, at the end of the fiscal year. It's going to 13 antennas, so it has a modest imaging capability. 13 2-meter antennas and 2 27-meter antennas that were pre-existing and are used to calibrate the small antennas. And it will be frequency agile from 2 to 18 gigahertz, sweeping across the spectrum once every second. So some of this design work was motivated by FASR design and development work. It's about a 10% of a FASR, or the FASR A high frequency subsystem. The science that it can address is some of the pathfinding science for solar flare and active region mapping, as well as sort of ground truthing some of the coronal magnetic field and plasma diagnostics that we have in mind. And the current status right now is that the 3 antenna prototype is up and running. 8 2-meter antennas have been installed. 5 other antennas are being refurbished. All the front-end, back-end electronics will be installed next month, and it will be operated as a community instrument. So here's an example of the kinds of things it can see. So compact, bright sources. So here's a model flare loop at frequencies from 1 to roughly 18 gigahertz in these first 2 columns. And then if we fold them through the instrument response function, you get these maps on the right side. And you see that, you know, they do a pretty good job, except at the lowest frequencies when we run out of resolution. But there are ways of dealing with that. If you take a particular map and then you have a spectrum at each of these points, so here are the spectra along each of these lines of sight. You can now fit both X mode, O mode, or RCP, LCP, and extract the parameters of the source. Here, for example, at this point, foot point, the magnetic field is about 680 Gauss, whereas up at the loop top, it's more like 145 Gauss. So it's really quite a promising and powerful technique. Ultimately, you want to do all lines of sight and extract, you know, fast electron distribution, the power law index, the magnetic field strength, magnetic field orientation to line of sight. In this sense, radio is unique. In, you know, it has access to non-thermal radio sources, and as I said, you see when and where the fast electrons are present in the source and can use those electrons to identify these other physical parameters of interest. Let me now turn to the, remember I showed you the figure showing schematically that above a few gigahertz we have incoherent gyrosynchrotron, which is packed full of information, which we think we can extract. Things are a little bit more complicated at low frequencies simply because the mechanisms themselves are not fully understood. I'll very briefly show this. I've just deciding I'm running out of time, and the discussion of this flare is actually kind of technical because there are only 3 antennas involved, and so to extract the information took a bit more. It was one of the great big powerful X-ray flares from the December 2006 period, where it had lots of coherent emission in the decimeter wavelength band, and we observed a burst like this, which for obvious reasons is called a zebra pattern burst. And here's a cut of what the spectrum looks like. You sort of see these quasi-regular bands of emission. So what's going on? Well, this is the FASR subsystem testbed, comprised of just three antennas. But with 3 antennas, you actually do extract spatial information about the source. You can triangulate and locate the source position. You can also put some constraints on the source size. I'm not going to go through those arguments because they're fairly detailed, but here again is a dynamic spectrum, but here and here are dynamic phase spectra, and you can see right away that because you see deviations in phase for the zebra that it has spatial structure. So I'm not going to go through all the arguments. Suffice it to say that going in, there were about 10 different theoretical models for this particular phenomenon. And we were able to winnow them down to a particular model called double plasma resonance, where the frequency that we observe is the upper hybrid frequency, which is this combination of the plasma frequency and the cyclotron frequency. And so that's one resonance. Frequency is resonant with the upper hybrid frequency, which is itself resonant with a harmonic of the electron cyclotron frequency, hence double plasma resonance. So because the cyclotron frequency is in general much less than the plasma frequency, we basically have a resonance between plasma frequency and the harmonic of the cyclotron frequency. And we did some fitting on the data. We were able to actually identify the harmonics of those stripes I showed you. They were basically 8 to 13. So we had a precision measurement right away of the coronal magnetic field using the harmonics of this particular type of double plasma resonance plasma radiation. We actually did some extrapolations, some nonlinear force-free field extrapolations. Yujing did those with us. Again, this is a little bit going far afield, but we have a line of sight through the source, but we don't know where along the line of sight that the coronal source appears. This was used to sort of come up with a list of plausible locations, and we found that for deep projected positions, possible values range from 30 to 90 Gauss over a height range of 40 to 80 megameters, which were fully consistent with the fitting that we did, the forward fitting that we did. And then I'm going to spend just a few minutes on one last example from the Very Large Array. Some of you may be aware and some of you may not be aware that it's just gone through a major upgrade in performance, which has led to an increase in sensitivity by more than an order of magnitude. So for the nighttime people, it's really a boon. It's a brand new instrument. For people like us who look at the sun, because we're perverse, the sensitivity does us no good whatsoever, because the sensitivity is, the system temperature, the receiver noise is completely overwhelmed by the sun itself, right? So normally we have these beautiful cryogenic systems with receiver temperatures of 20 Kelvin, right? Liquid helium cooled, and we kick it up to, 20,000 degrees by pointing at the sun. So disturbing. But one of the huge boons for us, though, is that the instrument's been broadbanded. So it now has continuous access to frequencies from 1 to 50 gigahertz. It used to be we only had spot frequency coverage, and the bandwidth was just 50 megahertz, just very slender. And now, so at L-band, so 1 to 2 gigahertz, we can get the entire thing in one shot, an octave of bandwidth, and we have a very powerful correlator to do the spectroscopy. So in the case of the sun, we now have frequency coverage from 1 to 8 gigahertz available now under shared risk observing, and in a few years, 18 months say, we'll have all the way up to 18 gigahertz. Now the downside is that 1, we don't have access to the telescope very often. 2, the antennas are too big. 3, they're too few. And then it's not frequency agile. We can't change frequencies fast enough to do real imaging spectroscopy. But if we pick a given band, we can. So here's some early data that some of you have seen, others perhaps not. It was published just earlier this year in the AppJ. These were commissioning observations in late 2011 in the most compact configuration. We only had 17 of the 27 antennas, 1 to 2 gigahertz, 1,000 channels, dumping every 100 milliseconds, and dual polarization. So if you think about it, every 100 milliseconds we were getting 20,000 snapshots, which is a lot of data, it turns out. Now we timed things perfectly to miss the big flare here, and we observed right in this notch. So beautiful. We may have saturated our electronics had we been pointing at this time anyway. But what happened in this window here was a nice EUV jet, soft X-ray jet occurred. So a magnetic energy release event occurred, and we were able to observe it with the VLA. So what did we see? Here's a map. Along the bottom is hard X-rays, and there's the jet there. Okay, and there it is again. And the radio, so now we're again dynamic spectrum. Here high frequency is low, 2 gigahertz down to 1 gigahertz. This is just 30 seconds of data, and you see all these little decimeter wavelength type 3s. So we're seeing a bunch of electron beams released in association with this X-ray jet. Now unfortunately, we lost half the band to most of the antennas due to a hardware fault. That happens when you're commissioning instruments. But nevertheless, we still had lots of type 3s to look at. Zooming in on that particular part, here's the cross amplitude, and here's the cross phase spectrum. And you again see that there's structure and phase, meaning as a function of frequency, meaning the source shows a change in position as a function of frequency. And but now, unlike the FST, we can actually map that out. Here's another summary figure. Here's 3 different snapshots of the jet evolution. So you see the thing come out and then form this nice arch here. Here are the type 3s. And then here in blue is the VLA integrated radio flux, and in red is the RESI hard X-ray 12 to 25 keV. And you see there's a very nice correspondence. Why should there be? Well, there's magnetic energy release that heats and blows off plasma. I'll show you in a moment in the movie that there is in fact a hard X-ray source down at the foot here of the jet. Electrons stream down and create that hard X-ray source, and at the same time electrons stream up and produce the type 3s. So it's perhaps not too surprising that there is a correlation between the two. So again, we're looking at the jet and the formation of this arch. Would anyone care to speculate what the type 3 electron beam trajectories are going to be?
Straight at you.
Well, okay, so what I'm going to show you next is, again, the movie. What you'll see is, in color, the position of the type 3 emission at any given time. Blue symbols indicate low frequencies, red indicate high frequencies. It's in a spectrum distribution. And across the bottom, you'll see the hard X-rays again.
So here we're looking at thermal electrons.
Here we're looking at thermal plasma.
And then what you're going to show us, we're looking at gyro stuff.
No, you're going to see plasma radiation. Suprathermal electrons, sort of less than 20 keV electrons, are driving this. So let's look at that. There's the hard X-ray and contours here. These are the type 3s. And you see that they're highly erratic, but they sort of mark out a channel. And let's see if I can get that to go again. There it goes.
Can you say again? I understand, I think by the STO data, that's sensitive to the bulk of the distribution function electrons.
Right.
The colored rapidly moving things on that are sensitive to suprathermal electrons below a certain energy. That's what you said.
Right.
But they are, in essence, this is way higher than the average thermal energy electrons.
That's right. Well, yeah, I mean, they're a few keV up to no more than 20 keV. The electrons which are streaming away from the magnetic energy release region,
They're 10 to the 8, 10 to the 10 Kelvin or something.
Yeah, but they're highly, it's a beam. The beam is unstable to two-stream instability, which produces plasma waves, which then are converted to electromagnetic. So here's the neat figure. If we sort of add up the contributions of all those little type 3s popping off, we get this distribution. So here's the hard X-rays near the foot of the jet. You see this big range of heights from low frequency to high frequency. And then here's some snapshots from that movie that I showed. So this defines sort of an envelope of trajectories in the sun's corona along which these non-thermal electrons streamed away from the energy release site. And it has absolutely no counterpart that we can find in the thermal.
Oh, good.
So let me say a few words about interpretation, and I'll wind it up. Harmonic plasma radiation. We could assume some fundamental, but we assume harmonic for two reasons. First, fundamental plasma radiation is much more strongly subject to collisional damping. It's harder to escape from the corona. Secondly, the degree of polarization, which I didn't really show, is moderate, consistent with harmonic. What was the third thing? I forget the third thing. I just did a Rick Perry. But if it's going to be one or the other, right? It's going to be fundamental or harmonic. The density will scale accordingly. We just get into bigger trouble if we assume fundamental, for reasons I'll get into in a moment. But right away, that tells you what the density is along that trajectory. It ranges from about 3 to 7 times 10 to the 9. Okay, pretty high, very high density. Distributed over heights ranging from 30 to 80 megameters. We can plot all of those points up. It unfortunately cut off at 1.5 gigahertz for reasons I mentioned, the hardware fault. But we can sort of assume a barometric atmosphere, infer a scale height about 40 megameters, corresponding to a temperature of about 1,000,000 degrees in the corona above this jet. The type 3 frequencies sort of bobble along around this vertically, which implies that in fact there's a good deal of inhomogeneity transverse to these trajectories. In other words, from field line to field line, the density can change by tens of percent. But as I mentioned, there's no trace of a counterpart to the non-thermal type 3 emitting sources seen in SDO AIA images in any filter. Okay? So that means that there's the background emission, which is very diffuse and low, but we see no enhancement, we see nothing in absorption. So what does that mean? We know the density, right? So we go through some arguments. You can go look at the paper if you want to see it in detail, but we're able, using, I forget how many sigma we assume to get a limit of 40 to 100 data numbers per pixel above background. So we infer a limit of 5 times 10 to the 25 for column emission measure. And so you can go through the arithmetic and find that a given filament along which these fast electrons are propagating can be no more than about 100 kilometers in diameter. So you need highly non-subarc second resolution to actually see them. And it gets even worse. That's if one pixel is occupied by one filament, right? If we assume there are n filaments, which is more likely the case, then the diameter of these filaments is going to drop down by root n. So it's extremely fine filamentary structures in the corona.
What's the electron gyro radius in meters?
It's tens of centimeters. Yeah, it's tiny. So this is not new. I mean, this has long been known. It's long been suspected. There are other reasons for believing that the corona is highly inhomogeneous and filamentary in structure, but this is a rather more direct confirmation. So I hope I've convinced you that there are interesting things to see at radio, and in particular, using dynamic imaging spectroscopy, you can learn a great deal. So let me just conclude with a few remarks looking forward, because this is no secret that in the long term, we want to go all in on imaging spectroscopy and build an instrument that is in fact designed to do imaging spectroscopy. The example I showed you from the VLA is just 1 gigahertz of bandwidth. The FASR will go from 50 megahertz, so a wavelength of 6 meters, all the way up to 21 gigahertz. So nearly 21 gigahertz of bandwidth, spanning emission from the middle chromosphere all the way up into the middle corona and higher. So what this basically gives you every second is a 3D snapshot of the sun's corona and everything that's going on in the corona. And in fact, FASR, if you restrict your bandwidth, can go as fast as 10, 20 milliseconds. And again, we want to try to mainstream the use of these data. We don't expect people to be black belt interferometrists. Science data will be given to the community, sort of the way Yoko mainstreamed X-rays. We hope that FASR mainstreams the use of radio data. The kind of instrument it'll be, there's no Bayama radioheliograph, lots of little dishes. Why? Because you want to see the whole sun. You want lots of Fourier components instantaneously so that you can, in fact, image in snapshot mode the complex radio emission that you see. So FASR itself will comprise 3 different antenna systems to span that very large wavelength regime. Here's some out-of-date parameters, 3 different arrays. This one in particular is out of date. We can probably now gobble up 1 to 2 gigahertz of bandwidth simultaneously. The cost of processing such bandwidth has crashed. When we first began scoping out FASR and characterizing the correlator, sort of the brain that does the imaging, it was going to cost us $20, $30 million to build the correlator. Very expensive. That cost has now dropped precipitously to more than the order of magnitude. We might be able to build our correlator for about $1 million. It's amazing. Science, I've shown these slides lots of times. It's not just flare physics. As I said at the outset, we want to go after coronal magnetic fields in a big way, everywhere from quantitative measurements using a variety of techniques, flares, active regions, coronal mass ejections, and so on. The evolution over a variety of timescales of these fields, coronal seismology, and so on. I gave you some examples of high-energy solar physics that we can approach with this, but you can do much, much more with real imaging spectroscopy. I didn't really talk about drivers of space weather, but we'll be able to image the synchrotron counterpart to coronal mass ejections. We can image the associated shocks through the type 2 radio burst, prominence eruptions, and so on. Again, returning to this point, I think that it bears repeating that by observing the entire atmosphere all at once, by capturing all of the various phenomena that are happening simultaneously from the chromosphere up into the corona, we'll see it all tied together as a coupled system. Rather than seeing a CME in isolation, you'll see the associated flare, the filament eruption, the CME, the coronal dimming, the type 2 radio burst associated with the shock, and so on, all at the same time. And I think that's going to be one of the most powerful aspects to such an instrument. It's not limited to active phenomena, excuse me, the thermal solar atmosphere. We can go after with an instrument like FASR, solar wind. I alluded to the polar cap brightenings, the coronal hole brightenings in which fast solar wind originates. Even synoptic studies. Is it true, Stephen, that F10.7 is still the most in-demand data product from the data?
Either that or sunspot number.
That's right. It's rather homely. It's a proxy for, the incident UV radiation on the upper atmosphere. We can develop, precision proxies with an extremely well-calibrated instrument like FASR to do synoptic studies of that type, radiative inputs to the upper atmosphere, dynamo statistics, and so on. So with that, I'm going to stop. Thanks.
Questions for Tim?
Could one use FASR at night for something?
We have talked to our nighttime colleagues about that. For FASR A, the high frequency system, which is all the little 2-meter antennas, probably not much. For FASR B, the mid-range, those will be 6-meter antennas, and there'll be of order 60, 70 of those. For a few extra pennies, you could cool those front ends. In fact, it would be a very capable nighttime instrument. And then FASR C, which is a low frequency instrument, we might not even build FASR C. Why? Because there's a lot of activity right now in the radio community building low frequency arrays. There's the Murchison-Whitefield array in Australia, there's the long wavelength array in the United States, there's LOFAR in the Netherlands, and other telescopes are in the planning stages, such as something called HERA. Much of the physics motivating these instruments is cosmology, going after the epoch of reionization, for example. But the nature of these instruments is such that we can also piggyback. And in the daytime, when the ionosphere is a mess for doing cosmology, we can do solar and heliospheric science. So the short answer is that yes, there may be some promise for part of FASR for nighttime science.
We have a follow-on question on that. Our SIBO has been used to study ionosphere of other planets, and I wonder if there's any possibility of using that to study ionosphere of, say, Venus or Mars or anything like that.
Let's see, they typically use, don't they use occultation experiments to probe the ionosphere of other planets?
I don't know the details.
Yeah.
VLA is probably better just because it's
the VLA has the raw sensitivity over this wavelength regime from 1 to 50 gigahertz.
I know that there's one important instrument I think purposely left out, but and the operational modes for ALMA are not known. For solar, probably very well at this time.
Oh, well, funny you should mention that. Because, in fact...
I have a question later.
Okay, and actually, yeah, ALMA, I'm glad you raised it. It's a different kind of animal. For those of you who don't know, it's a big radio telescope, except it operates at millimeter and submillimeter wavelengths. And so it's going to be doing physics of dust in the universe and cosmology and astrochemistry, because lots of molecules emit lines down at that regime. And it was in fact configured or designed to point at the sun. You can point at the sun without damage, but we haven't worked out the calibration modes yet, the observing strategies. And so we did put in a proposal for a development study to position the community to take advantage of cycle 3 observing with ALMA. And so I, in fact, expect to hear about that in the next, by middle of October. And the European community also put in a proposal to European Southern Observatory to do exactly the same thing. And so we'll be pooling our resources. You know, we have interest on the part of many people, actually.
I had a lot of meals with Al Wooden this summer.
Oh, yeah, okay, well, sure, yeah. He's the ALMA project scientist.
So that's why I know that the solar modes have not been defined at this point for cycle 3.
Correct.
But in your wildest dreams, would you, if you're looking at a solar flare snapshot mode in the optically thin over past the turnover frequency, could you use it to do frequency synthesis to improve your spatial resolutions of fine structures?
Well, ALMA will be able to image solar emission at subarc second resolution. We don't have to worry at those high frequencies about scattering of our radio emission that we do have to worry about lower down. Looking at a flare or a prominence or the chromosphere, those are all dynamic phenomena, and that's the enemy of synthesis imaging. You have to sort of, if the thing is changing on a short time scale, you can only do snapshot imaging. Now, ALMA does. The good news is it has 64 antennas, and so that means it has about 3,600 baselines.
Yes.
So it has 20 times the number of Fourier components instantaneously to do the imaging, and it has a much smaller field of view. So in fact, you can do a pretty credible job of snapshot imaging a small field of view.
Well, let's keep our fingers crossed.
Yeah, stay tuned.
Do you know what is the origin of the rightnings of the solar poles? Are they related to polar plumes or something like that?
The short answer is no. But people have thought about it a little bit, off and on. They've been known for several decades, actually. The polar brightenings appear at frequencies above about 15 gigahertz or so, and extend up to maybe 40 gigahertz. By the time you get up to 80 gigahertz, you no longer see a contrast. So this is sort of a chromospheric range of frequencies that you're probing. You're also seeing it at a large angle relative to the local field. So the field is strongly implicated, but in terms of understanding in detail the origin of that brightening, I would say that I haven't seen a convincing analysis.
So many years ago, when we did this decadal study, and LOFA was one of the projects also considered for the US, there was this argument that solar observations in those frequencies were actually only done in the 60s, before people knew that there were coronal mass ejections and what their significance was to space weather events. Now, there is more capability by now. How much of that promise of the low frequencies has been materialized by now?
Well, not to take anything away from our European friends, but I would say that LOFAR, it's going to do wonderful things, but I'm skeptical that it will do wonderful things for the sun. Why? Because the configuration of elements on the ground, which, you're sampling the aperture plane with your telescopes on the ground, is non-optimum for solar work for the most part. Now, it does have a core configuration of a limited number of elements, but the resolution is not going to be particularly good. I think a more interesting instrument will be the MWA in Australia. And possibly, there's a fellow named Greg Hallonen, a young faculty member at Caltech, who is building out a low-frequency array from 20 to 80 megahertz, so that's a meter wavelength, so that's well up in the corona. That may have some interest as well.
So are you saying that at present there is no substantial progress in our understanding of these low frequencies, what the sun is about?
I would have to give you a very long answer over beer, Michael, because I would say that, in fact, there has been a lot of progress made in the decades since the 1960s. But as far as having an instrument that's been optimized to go after this in a big way, that is not yet available.
What limits the lowest frequency? Why is it 50, not 20?
Well, I suppose that's another lengthy answer. The original, I'm kind of hoping, frankly, this is me personally speaking, I'm kind of hoping that some of the other low frequency arrays can fill in for us below 100 megahertz. Why 100 megahertz? Well, 80 to 110 is the FM broadcast band, right? The light pollution in that band is horrible. So below FM band, you also have other issues, for example, with the disturbed ionosphere. Below 30 megahertz, the ionosphere becomes a real problem. You know, the sun will be dancing around on the sky as it gets refracted around by the ionosphere. So I would prefer that somebody else dealt with frequencies below 100 megahertz and that FASR itself dealt with 100 megahertz on up to 20 or 30 gigahertz. But that's not to say that there's not interesting physics. The reason that there's a limit is that you know, the ionosphere itself is ionized layer above the Earth, and the plasma frequency in that layer is about 10 megahertz, give or take. So that means that wavelengths outside trying to come in and, you know, incident on the ground can't make it through the ionosphere, so there's a hard cutoff there. So you have to go up in space and use spectrometers up there if you want to observe. In fact, they do exist on stereo and wind and IC3 and so on.
Highest frequency is like 30 and 14, so there's always a gap.
Right. What's Stuart Bale's instrument on SPP? Does that get up higher? Solar Probe Plus, I think, may span, but the gap has been narrowed, meaning you can trace things from the ground and then there's a little gap and then you see them out in the interplanetary medium. So, okay.
Thank you.
Thanks.
Thank you.